question is, where did those acid chlorides come from in the first place? So how do we go from an unreactive carboxylic derivative, the carboxylic acid, to the most reactive acid chlorides and acid bromides? So we're going upstream in the reactivity series. We'll just use acetic acid as an example. And we're trying to make it into acetyl chloride. Right. So basically, we're trying to take an OH group and convert it to a chloride. How did you do that when it was an alkyl group? Same transformation, right? Hydroxyl group to chloride. So if you know how to do the one on the right, which you should, maybe the same type of reagent will work for the one on the left. Quickest way to make this acid chloride, of course, is to order it from Aldrich. 1-800 Aldrich is always the solution to synthesis problems if you don't know the answer. But what if Aldrich doesn't sell the acid chloride? You actually have to make it. Or it's in the exam and 1-800 Aldrich will not get me very many partial credit points. Dr. Fink put that on the final exam. 1-800 Aldrich. I think I gave him like a point for amusement.
I'm going to ask him about that.
Dr. Fink took OK from me.
Oh, yeah.
So did Dr. Hermanowski, for that matter.
Oh, my gosh.
Yep.
That's hilarious. I need to work with
I've
him.
been here a while. Dr. Bryce took biochem from Dr. Vaught.
Oh, my gosh.
Everybody took biochem from Dr. Vaught because he's been here since, I think, time began. Back when he used to write his brontosaurus to class.
Oh, my gosh.
So what reagent would you put in here if this was on the exam and you wanted to get points for it?
I think I would, can you protonate the oxygen and then do an SN2?
So you could use HCl. Aqueous HCl will convert an alcohol to an alkyl chloride. But that won't work here. That's not a good method for an acyl chloride or acyl bromide. Right? You protonate this oxygen to chloride, you come here, and then you try to convince hydroxide to leave, and hydroxide would say no. So what other reagents are out there that allow you to convert an alcohol to an acid chloride or an alcohol to an alkyl chloride? And it was actually particularly relevant if we had like a secondary alcohol here and we wanted to convert it to the corresponding bromide, but we didn't want to get rearrangement, right? If we use HBr for this, we're probably going to get a carbocation intermediate, and then we're going to get racemization, and that's terrible.
If you use a strong hinder, no.
If you use a strong hinder, you're going to get just elimination.
Yeah, no, just don't listen to that.
So how do you convert a secondary alcohol to a secondary alkyl halide, bromide or chloride, without getting carbocations, and thus without getting carbocation rearrangement? What was the reagent that we used for that?
Was it with Cl2?
So SOCl2 for the chloride, and what was it for the bromide? SOBr2 would work, but SOBr2 is expensive and it's not the most common reagent for converting alcohols to alkyl bromide.
PBR?
PBr2. So it turns out that SOCl2 will also do this. And SOCl2 is a liquid, so you can actually just use SOCl2 as your solvent if you need to. And it turns out that PBr3 will also do this. That's convenient. The mechanism is not going to be the same as the mechanism for the alcohol to the alkyl halide, but the reagent is going to be the same. And so if you're not asked for the mechanism, it's very easy. It's SOCl2 or PBr3. This is the acid chloride of sulfurous acid. Sulfurous acid is a stronger acid than acetic acid. The same thing that makes sulfurous acid a stronger acid than acetic acid makes sulfuryl chloride, or thionyl chloride rather, a more reactive acid chloride. So we are actually going downhill in terms of reactivity. We're going uphill in terms of reactivity of our carboxylic derivative, but we're going downhill in terms of reactivity of acid chloride. We're converting the more reactive acid chloride into the less reactive acid chloride. And as a result, right, say here, right, this is the acid bromide of phosphorus acid. H3PO3. So we make the acid bromide by converting those three hydroxyl groups to bromide. And phosphorus acid is a stronger acid than acetic acid, which makes the acid bromide of phosphorus acid a more reactive acid bromide than acetyl bromide. So we're going from a more reactive to a less reactive, but the more reactive to less reactive is the more reactive acid chloride to the less reactive acid chloride, the more reactive acid bromide to the less reactive acid bromide, and not the more reactive acid derivative. So what's the mechanism? We'll go over the mechanism for the PBr3 reaction on Tuesday because it's part of the Helmholtz-Zielinski reaction, which is a reaction at an alpha carbon. So this one I'm not going to do today. But let's think about what the mechanism for this reaction is. The other two products are gases, which also makes this reaction favorable because those gases, once they're formed, just evaporate and they're gone. So there's thionyl chloride. It's tetrahedral electron pair geometry, trigonal pyramid. It looks a lot like phosgene, except that it's got a lone pair on the sulfur because sulfur has more electrons than carbon. If you had to come up with a mechanism for this reaction, what would you do first?
Can you use the OH on the
Acetic acid?
yeah, and then attack the sulfur, which then makes it.
So Isabel is suggesting let's use the OH group here on the
But
acetic acid
never
to
mind,
attack the
sulfur-
sulfur and push a pair of electrons out into the oxygen. I'm buying this part.
Yeah, but I don't think that's gonna work.
But you've completely forgotten what we talked about Tuesday, when we talked about which one of these two oxygens is likely to behave as the nucleophilic
Right, but it doesn't seem right. Yeah, so would it be the top one?
So this oxygen is the one that has the large partial negative charge on it.
Yeah, but then the
So that
sulfur,
oxygen is the one that's going to react with the sulfur.
even though the sulfur has electrons on it already,
The sulfur has electrons on it, but it also has a minor resonance structure that has partial positive charge on it. So it has that lone pair, but that lone pair isn't the important part of the reactivity of sulfur. The important part of the reactivity of sulfur is the contribution from this minor resonance structure and the fact that there are 3 electronegative elements that are sucking electron density. So if you were to write this with bond dipoles, right, all 3 of those elements are pulling electron density away, you've got a large partial positive charge on the carbon. It kind of looks like this, right? Except that there's a sulfur here instead of the carbon. But you know that acid chlorides react by nucleophiles attacking the carbonyl group. Well, this is an acid chloride. So it's going to react by nucleophiles attacking the positively polarized sulfur. Pay no attention to those lone pairs. Those lone pairs are saying, we don't want to react. And sulfur is saying, dude, I got a positive charge. We're reacting. Go sit in the corner while I map out the adults talk. Show it from the oxygen. It doesn't actually matter whether you use the lone pair on oxygen to do the attacking and end up with this double bond positive on oxygen, or whether you use the pi bond and end up with positive charge on carbon. Both of those are legit. So it looks like that. And we've now got a trigonal bipyramidal arrangement on sulfur because we've got 5 bonds to it. So it looks like this. So that's a logical first step. Use the nucleophilic oxygen to attack the electrophilic sulfur. Perfect. Second step.
I feel like you want to make one of the chlorides leave.
Good leader group. One of them.
Oh my gosh, I forgot we had that oxygen there. I'm like, what can we do with the double bonded oxygen?
So this is the nucleophilic acyl substitution reaction. Right? It's an identical nucleophilic acyl substitution to the reaction of an acid chloride with a nucleophile. Nucleophilic attack wasn't leaving group. It's just happening at sulfur instead. Anything a carbonyl acid chloride can do, a sulfur acid chloride can do. SO2Cl2 would do the same damn thing, except you have another double bond oxygen instead of a lone pair. Now what?
Can you protonate the double bonded oxygen with the sulfur?
You should probably not protonate anybody because it's already got a positive charge.
Never mind.
Right? This intermediate has a positive charge, you don't want to put a second positive charge in.
Okay.
There's probably a method to my madness in throwing that chloride ion and throwing it where I threw it.
But it can't attack anything. Because it sucks. Oh, wow.
It can attack a carbon that basically has a positive charge on it already because the other resonance structure has a positive charge on this carbon.
Yeah, okay.
So you just booted chlorine off the sulfur and had it come and attack carbonyl carbons, right? So leaving group off sulfur, nucleophile on carbon. And that's pretty reactive now, right? Because of the minor residue structure that has a positive charge on it. So now what?
Now we want to protonate.
We've still got a good leaving group here. Sulfur has 2 oxygens on it
Yeah.
and starts thinking,
I think you want
it
to
would
put
be
it.
really nice to become SO2 gas. I like being gas. I want to be SO2 gas. So what's going to happen is the pair of electrons here are going to push in and form a pi bond and boot out that SO2Cl minus, immediately decompose this. So we're doing another nucleophilic acyl substitution effectively, but we're now doing it and that's where the SO2 gas comes from. And we got chloride ion. And we've got the protonated form of our acid chloride. Under most circumstances, it's a terrible idea to use chloride as a base. Usually, you don't want to use chloride as your base. But you're in a solution of an acid chloride, and you're not going to want to protonate that. Right? Acid chloride don't really like to be protonated. You've got acetic acid. It doesn't really like to be protonated all that much either. So chloride's going to take that off to form the product, and the HCl gas, which is the other product.
So is that irreversible?
You know, it's probably not coming back once the gas evaporates.
Okay, so we can draw the arrow one way. That's
Yeah, I'm drawing that reaction one way. Because, and really, I ought to be drawing, this one I should not be drawing two ways either. Once SO2 gas leaves, it's not coming back. So those steps 4 and 5 are really not reversible. Steps 1, 2, and 3, there's no reason why those can't reverse. In practice, they don't really, because the last 2 steps. Right? So we're driving this reaction forward by the Chatelier's principle, by removing a product as it forms because the 2 products are gases. It's a nucleophilic acyl substitution of sulfur, and then you're adding chloride to the positively polarized carbon, and then booting out your leaving group. So that's basically an acyl addition in step 3, followed by this decomposition, right? The decomposition of gaseous products. It's not the only reagent that will do that. SO2Cl2 would as well, and then the gas would be SO3 gas instead of SO2 gas. And actually, oxalic chloride will do this reaction. And I think in Klein, we might use this, oxalic chloride, which is the acid chloride of oxalic acid, or 1,2-ethane-dioic acid. This is a stronger acid than acetic acid. So if oxalic acid is a stronger acid than acetic acid, what does that tell you about the relative reactivity of oxalic chloride versus acetyl chloride?
it's worse. Oh wait, no, that's more reactive.
Sulfurous acid is a stronger acid than acetic acid, which means sulfur chloride is more reactive than acetyl chloride.
Yeah, so the
Same is true here. Since
Okay.
oxalic acid is a stronger acid, and it's a stronger acid because you've got this other electron withdrawing carboxylic group, which reduces this pKa. I think we have that up as like 1.5-ish from the table. So the acid chloride, oxalic chloride, is a more reactive acid chloride than acetyl chloride. Same principle, right? We're converting a more reactive acid chloride to a less reactive acid chloride. The other products in this case are also gases. Lots of gases. So one of these chlorides ends up replacing the OH, One of these carbons becomes CO2, the other becomes CO, carbon monoxide, and then HCl gas. I'm not going to go over the mechanism for that one. I think this reaction, the acid with the oxyl chloride form the acid chloride of these three gaseous products, I think it's inclined, it's not an out-test rule. But it's the same principle. Any acid chloride, in principle, that's more reactive than the acid chloride you're trying to make should be able to convert it into the acid chloride. If you also have gaseous products, then you have a Le Chatelier's principle reason for that reaction to go in the forward direction and not go in reverse. Let's take our break, and then we'll come back and talk about just basically reactions to memorize, organometallics and hydride reducing agents. In the pre-recorded videos, I did go through a lot of mechanisms for the acid chlorides, or sorry, for the acid derivatives reacting with organometallics and hydride reducing agents. I won't go over a lot of mechanisms today because I don't need time. We'll run through the reaction. And I think there's a summary for all the different hydride reducing agents and organometallics and the different acid derivatives. Summary sheet in the useful information on Blackboard. Let's take a break. I'll save this video.